want to talk about Newton's universal law of gravitation, and sort of we're taking this concept of weight and extending it to a much more general case. Now, as we've dealt with before, when we're talking about the force of gravity, at this point we've talked about the weight. We have a person standing on a planet, and this is basically the formula right here. Except instead of using the formula, instead of using W, which I shouldn't be using because that also stands for work, F with a subscript G here for the force due to gravity is equal to the mass times the acceleration due to gravity. If I'm on the surface of the Earth, 9.8-ish meters per second squared. If I'm on the moon, it's about 1.62 meters per second squared, somewhere in that range right there. So G is not a constant, but we pretend for the first 8 chapters of Hewitt's book. And so now we need to take it to the next step. Now, that's just a specific case of a much more general formula right there. Now, if you think about it, if you start with the idea that any two masses are attracted to each other, that since forces don't play favorites, we can't assume that the Earth-human relationship is different than the human-Earth relationship, that we're just masses somehow attracted to each other. And also because of Newton's third law, that I should be able to interchange the masses, and I should still be able to get the same value. And so from a math point of view, whatever the formula is, that means I'm either adding the masses, because the order in which I add doesn't matter, or I'm multiplying, because the order in which I multiply doesn't matter. But it has to depend upon both, because of Newton's third law, and one of the commutative properties has to hold. So we end up with this relationship here. So we have the two masses which happen to be multiplied that make a difference. Now this R right here, this is the distance between the centers of mass. And so that becomes very important. Now, one of the ideas, well, we'll talk about the exception in just a moment. So if I have talking about the Earth Sun, I'm talking about center to center. Earth Moon, center to center. I'm not talking surface to surface. Now, when we're talking about human Earth, we're talking about not the ground, because we're really close to the ground. We're talking about the center of the Earth, the gravitational center of the Earth, as well as gravitational center of humans, which is somewhere waist area. So that's the formula right there. Now G right here is just a constant. That is a value that depends upon the unit system that you're using. It is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Different units. There's also something called naturalized units in which G is equal to 1, but that's theoretical physicists where they just hate writing that much that they just start making things equal to 1. So that's the force due to gravity. So this right here is the more general formula of this right here. So let's take a look at a particular situation of, since those are supposed to be equal, let's take a look at person standing on the Earth or on some planet. So that's a P right there with an M1. So the mass of this planet is M1. The mass of the person is M2. Now the size of the planet is huge compared to the size of the person. So this is not drawn to scale. That's key for this, for the next bit. It's not drawn to scale, and so the distance from the center of the planet to the center of the person is so close to just the radius of the planet that we're not losing a whole lot. Multi-million-dollar equipment, it matters. In everyday life, it doesn't matter. So the distance from here to the surface and here to the center of the person, really, it's not that big difference. And so if I take that, therefore the weight of the person, mg, should be equal to the gravitational force between these two masses. And so therefore, we should be able to equate those two equations. This is the more universal equation right here, and this is the formula for weight. Now notice that this is m2g because the person was mass 2, and we're talking about the weight of the person. So that allows us to come up with the formula for the acceleration due to gravity. And so if we just divide both sides by the mass of the person, because the mass of the person really does not affect acceleration due to gravity, that's that whole drop two objects of different masses, they fall at the same rate, that we end up with this down here. We have the acceleration due to gravity is equal to just g times the mass of the planet over the radius of the planet squared. And so now I can take any mass and radius of any planet, and I can, or moon, or any large object, and I can now find this acceleration due to gravity for those. I think that's actually pretty cool. But then again, I do physics. And I think that's where I was going to end it right there. So that's just a quick blip on universal gravitation. Now the question is, I do want to throw in one other concept here, this idea of G. It is called the gravitational constant or universal gravitational constant. This whole idea of dark matter and dark energy back years ago, a couple decades ago, when I was first starting out looking at this stuff, that it was actually a question whether it truly is universal or not. And as a matter of fact, some books even drop the word universal at this point, just call it the gravitational constant. Actually, I think most books do at this point. But they were trying to figure out why the universe was behaving the way it does. And so that was one of the things they looked at was that value of G a constant? And at this point, I think they're still sort of working with the fact that capital G there is a constant. Please don't confuse the capital G with the lowercase g. But the capital G is a constant, but there's this other stuff out there that's what the dark energy and dark matter is, and there is experimental evidence for that. Check out the TED Talks on that. I think really good TED Talks. Well, then again, I haven't watched a bad TED Talk. If you're not familiar with TED, it's TED.com. Be careful, you'll get hooked, and even though you'll learn a whole lot of stuff, your family might not see you for a while, for better or for worse.